So, welcome everyone. It is my pleasure to introduce today one of our wonderful mathematicians, Nader El-Khatib, for a talk on mathematical modeling of atherosclerosis. Thank you so much for joining us this afternoon. It's wonderful to also see undergraduate students on this call, as well as colleagues from various parts of the university and our own School of Arts and Sciences faculty. So when you're ready, Dr. Khatib, we're all ears.
Thank you very much, Dr. Jnanati. I welcome you. Really, I'm happy to see you here. It is a great pleasure to share with you our findings in terms of, as Dr. Jnanati says, mathematical modeling of atherosclerosis. So first, let me just verify something, if I am sharing the good slide or the bad one. Okay, this is the good one. But it is the same title. Okay. Can you see everything? Okay, great. So let's start with the motivation behind this problem. So actually it's very simple. If you ask Google, what is the #1 cause of death in the world? The answer is more than obvious. It's the cardiovascular diseases, as you can see them here. So cardiovascular diseases are the top cause of death, even if you may think that cancer is the first in terms of ranking with respect to deaths in the world. No, cardiovascular diseases are the #1. Now, also we will ask our new collaborator and very intelligent one, ChatGPT. So if we ask him or her, what is the #1 or the top cause of death in the world, the answer is obvious with some explanations and some data. You can see, for example, let's see again here. So the numbers are very clear. We have about 80 million deaths worldwide in terms of cardiovascular diseases. However, for example, cancer is in the second position with only 9.6, so it's almost like the double of the number. So this is why we are interested to study this, to understand what is behind, to understand the behavior, if we can predict some in the future, some very dangerous effects, some very perhaps actions to take prior in order not to be in this dangerous situation. So what is atherosclerosis? I will start with this figure, with this very nice, for the biologist, figure. I hope they are very happy with this. This is a cut of the artery, and we can see that normally the artery, a healthy one, if we look at it as a tube, this is the healthy one. We don't have anything inside. We have the blood circulation as it is shown here. All the nutrients, all the blood cells, white, red blood cells, the plasma, everything is circulating normally. However, when atherosclerosis occurs, it leads to a fatty deposit within the wall of the artery. And this fatty deposit is full of fat and other molecules and elements. But the most dangerous effect of this fatty deposit is that it renders the lumen of the artery to be narrow. And this narrowing has the dangerous effects on the human being. So for example, if we talk about the important artery in our body, which is the carotid artery. The carotid artery is the artery that leads blood to the brain. If atherosclerosis occurs in the vessel wall of the carotid artery, this leads to the narrowing of this carotid artery so that feeding, let's say, brain with blood will be affected and will be reduced. More than this, not only the lumen, you can see this this let's say, accumulation of cells here, this is the result of the rupture of this lipid core. This lipid core, when it enters in interaction or in contact with blood, with every heartbeat, you know that blood circulates with every heartbeat. So at every heartbeat, if it enters into contact with blood, blood may exert a pressure or a force on this, and since it's a solid, if you push, let's say repetitively or periodically, it may render to what? To the rupture of this. And the rupture is very dangerous because, as you can see, some solid parts can come out, and then a total obstruction of the blood vessel may occur. And this is unfortunately fatal if it turns out that it's happening in the carotid artery going to the brain. This is what we call a jalta dmaghi. It is when blood totally obstructed. We don't have any blood in brain, so actually this is very dangerous. So as you can see, the effects or the results of this formation of the lipid core within the arteries wall is the main dangerous part in the phenomenon. Now we will move more in depth into the biology of this. So here what we did is the following. This cut that we had before, we cut the artery. So actually this is a plan, the screen that you are seeing shared on your screen is the plan of what we have got. So this part here, this domain is where blood circulates. This is the first barrier between the blood and the wall, the artery wall. So here we are inside the artery wall. It's a part called the intima. We have several layers. The layer we are interested in is called the intima. We have other layers actually. And within the intima, everything that we have seen before will happen. So what happens is the following. For example, due to stress, due to an injury, due to some dysfunction in this layer called the endothelium here, these yellow, I guess you are seeing yellow, yes, yellow cells are called endothelial cells. So due to some dysfunction, that can be, as I told you, an injury or stress in the artery tissues and all these, the low density lipoproteins that we will denote by LDL, which, as you know, cholesterol is what? Is, let's say, split into two types: bad cholesterol and good cholesterol, as known as HDL, the good one. The bad one is LDL. So if this dysfunction of the artery occurs, then molecules of LDL can penetrate through these cells and go inside the intima here. When they go inside, they undergo something called oxidation. They are oxidized. We call them ox-LDL. We will call them ox-LDL. But the problem is, when LDL is oxidized, it's ox-LDL, it's considered as a dangerous agent for our human body. Hence, what happens? We call the cops to eliminate this. Who are the cops? The monocytes, or the white blood cells, or the immune cells. Let's put them under the umbrella immune cells. So there will be an immune reaction. We call for the immune cells. They will come, they will adhere to the endothelium, and they will roll, actually, they roll like a ball or like a bubble under this. And then when they find a way, they enter, they transform into macrophages in order to be able, macrophage is the cell that can come and phagocyte or eat or eliminate what? The ox-LDL. Once it eats this ox-LDL, it is transformed here. This is the new molecule, let's say the macrophage with ox-LDL. Later on, they are transformed into a foam cell. The foam cell is actually like its name, it's foamy a bit. Okay, its nature is foamy. So the accumulation of foam cells, if this phenomena is repeated, if we have a lot of LDL, a lot of oxidation, a lot of call for COPs they come, the monocytes, they come and they eat, this auto-amplification phenomena will lead to an accumulation of this, all these fatty molecules or material inside. That's why, look, the artery is a bit deformed, and we will get step by step or slowly, we will get this lipid core within the artery. Then, in order to cope with this, body has a lot of ways in order to cope with that. So, for example, in order to call for more monocytes, the body generates something called cytokines. They are here. So cytokines are also two types. Cytokines can be pro-inflammatory, but they can be also anti-inflammatory. Pro-inflammatory, they will accelerate this phenomena. That's why I talked about auto-amplification. They will call for more monocytes in order to defend our body. And anti-inflammation will try to inhibit this phenomenon. Why? In order not to have it with an auto-amplification infinitely, because we have to a little bit inhibit this. So there is somehow an equilibrium between the auto-amplification, let's say, led by pro-inflammatory cytokines, and what? The inhibition led by anti-inflammatory cytokines. So here comes like a kind of inhibition, as I told you. Then later on, in order also to put a barrier for this, well, because it can go for the whole artery, it can go, in the length of the artery, it can go from the brain until our feet. So, in order to, let's say, bound this, what happens is the following. These SMC, SMC for smooth muscle cells. These smooth muscle cells, what they do, they migrate and they come and form a fibrous cap over this deposit so that it's limited inside. Okay? So what we obtain is something like the following. So inside the artery, here is the lipid deposit, and as you can see, these are the smooth muscle cells. They come and they form this barrier. But this is, as you can see, is obstructing a bit or reducing a bit the lumen of the interior of our artery. Okay? And this is what we will study now. These are actual figures. As you can see here, this is a cross-section on the left of an artery where look at the part of the lipid deposit. Normally a healthy one should have all this lumen, but we have only this part where the blood can circulate. Okay? All this has been what? Full of lipids and all the other molecules. And this is actually a cut for the carotid artery, because the carotid artery has a bifurcation. It's not a straight tube. Let's say we have a bifurcation of two tubes that goes, and here is the accumulation of the lipids inside the carotid artery. So we will mathematically describe the first phenomenon. What I mean by first phenomenon is the setup of the inflammation. Now, so this model is formed by two partial differential equations. These partial differential equations are of a specific type. These are reaction diffusion equations. What do we mean by reaction diffusion? So this is the variation of the concentration of immune cells, because M is the immune cells that we call monocytes, if you remember, but we will put everything inside. So monocytes, macrophages, or immune cells in general. You will hear me repeating immune cells several times. So this is the variation of or the evolution of the concentration of immune cells with time. It depends on their diffusion within the artery, but also the interaction with other agents. What are the other agents? The cytokines, pro-inflammatory cytokines and anti-inflammatory cytokines, which are here designated by A. So this type of equation is the reaction diffusion, because we have a diffusion term and the reaction term. Okay? And both, they will play together in order to determine how M is evolving with time. But similarly, the second equation is the equation for A, which is what? The cytokines. Okay? So in order to model this, we have to choose, actually the diffusion part is ready. We have a diffusion. Both, they diffuse inside. But what about the reaction between them? The reaction between them is modeled through these two functions. So first function, which is of this type, is a fraction, let's say. Okay, it models what? Look at this fraction here and pay attention to this term here, alpha 1. This term in the numerator of this function is modeling, the whole function, actually f1 of A, is modeling the recruitment of monocytes promoted by cytokines. So the cytokines are driving this, okay? And this alpha 1 represents the function at the beginning, where the cytokines not yet are acting. Yani shu, when A is 0, put instead of A0, you get what? You get alpha 1. Okay? So this is alpha 1 for us. It represents what? The start. What is the start? The OX LDL present in the intima. When OX LDL, when LDL is oxidized, this is what triggers everything. So this alpha 1 is the quantity. Alpha 1, you will see that it will determine in which case we are a very dangerous one, an average dangerous one, or not dangerous at all. We will see that we will have 3 classifications later on. You see the numerator here. What is the numerator? The numerator is actually the effect of inhibition, because if you divide by 1 plus A over tau 1, you are reducing the quantity. Okay? So this is to model the inhibition. And tau 1 is a coefficient that represents how much time is needed in order to let this inhibition act. Okay? Now the other function, it's quite similar. It represents F2A here. So it represents, I will not spend a lot of time. It's really very similar. Production rate of cytokines, but due to what? Due to M, because as long as we have M, as more as we have M, as more we have pro-inflammatory cytokines, and vice versa. That's why it's auto-amplification. They are amplifying themselves by themselves. This is the term that we actually put here in order to model the inhibition. But which inhibition? The inhibition due to the migration of smooth muscle cells that they will come and put a barrier over everything in order not to let them let's say, evolve over the whole artery. So we consider this also as an inhibition phenomenon. ماشي؟ هلا, what about minus lambda 1m, minus lambda 2a? Minus 1 lambda m are the natural death or degradation of cells because they die. Okay? And similarly for other components. So we consider it as the natural death. هلا, if we want to study this, we start by studying something called the kinetic system. What is the kinetic system? The kinetic system is when we eliminate the diffusion and we study only the evolution in time. So we draw the isoclines. Well, it's technical mathematics. So we draw the isoclines. Why? To find the equilibrium and, well, equilibrium points so that we can study if they are stable or not. And if we do this, we will see that we might have three potential cases. I will start naturally on the left. Here, if we draw the isogram, for the first equation, I will get some F1 for the second table. These are big F1 and big F2, not the F1, F2 that are with us, okay? So we will see that there will be no interaction. And pay attention, kindly, pay attention to this point called Ni, and I will say why it's Ni. It's for non-inflammatory, okay? Why pay attention to this? Because look at the coordinates of these points. They depend on alpha 1. So, alpha 1, it models what? It models the initial quantity of ox-LDL that is present in the intima. That will trigger everything. So, if it is very low, this is the case that we get. If it is intermediate, this is what we get. And if it is high, this is what we get. Okay? With respect to each other. Very good. When it is low, nothing happens. We are happy. No intersections, no equilibrium, nothing will happen. Well, it is low so that you are pursuing a very healthy regime. You are doing sports. You don't have a lot of LDL circulating in your body. You don't have a lot of ox-LDL so that in your intima. Great. But what if you start eating a bit of French fries or, not very healthy regime? Here you might have an intermediate quantity of ox-LDL in your body. And what happens here is the following. We will get two intersections. Okay? These intersections are either this point or that one. That one is always an unstable point. If we study mathematically speaking, it's an unstable point. But in this case, this one is stable and that one is stable. So, if we trigger the system, it depends where we put the point. If we start with a point here and we trigger with time the system we called it what? The ODE system, the kinetic system. We might go toward this one, but also we might go towards that one. So it depends on the initial condition of A and M. So that either we go to a high quantity represented by this point of M and A, and this represents the inflammatory or the inflammation case, or we can go to low quantities of M and A, like here, and this represents what? The non-inflammatory. That's why I called it Ni. Very good. But what if this point is very high? Let's say sufficiently high so that it's above this straight line represented by F2. Then this point is unstable. So wherever you put your starting point, if you draw the isocline, they will go, here it's actually a demonstration, so we will see it. Actually, they go to this point every time we trigger the system. So let's start with, actually I didn't mention, but it is written, the middle case, the one in the middle is called the bistable case because we have two stable points, while the other one is the monostable because we have one, which is I. So, what if we trigger this? Let's start here, it's the bistable case. Here, I am below the threshold. As you can see, we go to the non-inflammatory one. Why? Because I am below some threshold. And this is the threshold that will determine if we are over the risk or under the risk of developing atherosclerosis. This is first. Now, if we are above, this quantity is sufficient so that we go to what? To the inflammatory case. But if we are in the monostable case, where this quantity is high, then even, look, I started with few quantities of M and A, because here the horizontal axis and the vertical axis, as I showed before, are A and M, okay, respectively. So even if we start here, you will see that we will go to the inflammatory case. I will trigger an inflammation. So what does that actually explain to us? It explains the following. For intermediate concentrations of cholesterol, we have a potential chronic inflammatory response. We have some threshold effect. So, well, we have to pay attention not to go beyond. But with high concentrations here, red flag. We need to change everything in our life, our mode, our diet, do sport, whatever. And if, of course, the first case is the most obvious one, low cholesterol, we are happy, we are doing the right thing. Very good. Now, this was for the study in order to deduce a biological interpretation, but now we need to go back to the partial differential equation because we eliminated the diffusion term. Now we will set it back. Okay? And here it's a definition just for to try to prove the existence of a traveling wave solution of this system. Because what? Actually, for this work, we collaborated with medical doctors, and medical doctors were interested to explain in the following fact. They wanted us to explain or to show that atherosclerosis, the inflammation of atherosclerosis, diffuse in the artery like a wave propagation. And this will be proved through the system because the solution will be of a traveling wave type. What is a traveling wave? Actually, so if we have a system like that one, of course, U here is a vector, so we have several components. For us, they are A and M for now. Okay, any two components. So they can be U1, U2, until UN, whatever. A traveling wave solution is a solution of this form, where C is the speed of the propagation of the wave. So W is a solution, and it connects here. We have the, they are stated here. It's W plus and W minus. These are the limits of Wx at plus or minus infinity. So here I have W minus, here I have W plus, and the wave will connect these two equilibria and propagate to this direction or that one. Okay? Very good. So, so we prove the existence of traveling waves in both cases, bistable and monostable, because due to the fact that the system is monotone. Actually, the monotony of the system is very, very useful. And numerically speaking, we will simulate this wave propagation when we start with an initial condition, how it will propagate. So what you have to actually to imagine here, of course it's not like this in true life, but it is describing how it is propagating. So the scale of time here is years. It's not مش بكره حيصير معي كوليسترول بهالسرعه. Okay, unless you eat all the McDonald's. So, very good. And here it's another result. Here actually we are showing that the threshold effect. So before, if we are above the threshold, we will propagate. And the next one is if we are below the threshold, we will not propagate. So it will inhibit, and you will see that it will collapse totally. No propagation, no setup of inflammation. ماشي? Now, in the monostable case, look at the initial, but حتى فوق مش مبين قد ما صغيرة due to numerical, let's say, inaccuracy in the rendering. You can see that even starting with this, we will set up what? A chronic inflammation or a wave of propagation. So this is how we describe, and if you want, we can summarize this by the following. So, for example, this model describes a chronology for atherosclerosis. Like, as you can see, if we are young, we are still, fine, young. We are not eating n'importe quoi, and so no inflammation. As long as we advance in age, the danger will be more and more here. So we have to take care of ourselves. We have to lower this alpha-1 in our body so that we don't risk having this inflammation. Now, as you can see, we didn't ask me why we consider only an axis and then a propagation over an axis. Because as a first approximation, we considered the intima, the layer of the blood where everything is happening. We consider it very thin so that it's only over an axis. Now, we will consider, as you can see here, the thickness of the intima as h, and the model will be a bit similar. These are reaction diffusion, of course, but we have x and y. Now, the domain is not only an axis. We have x and y. More than this, if you remember F1A that appears here right after the diffusion term in the equation of M, it will be actually put, the recruitment of immune cells will be modeled through a boundary condition over the upper boundary. That is here. It's now G of A. Okay, so here is the blood flow, here is the intima, the recruitment is through the boundary, through the G of A, and G of A actually is not a very nice function. It's a non-linear function. So the proof, well, we prove the existence through this theorem of traveling waves. There is a kind of technique. So first of all, we don't do it over minus infinity plus infinity. We cut the system at some point, we cut the domain at some point. Then we regulate the bound, because here we have irregularities on the corners. So we regulate them through a tricky mathematical tool, which is rendering them by putting circles on the boundaries so that it is regular. And then we actually, through two steps, we define first the equilibria, لأنه we go from an equilibria to other one. This propagation, it starts at some equilibria and goes to other one. That's why it's kind of propagation, and it will, here we will have nothing, and it will be set up later on the higher equilibria. So we define the equilibria and then prove the positivity of solutions, deduce a comparison principle so that it leads to the existence of solutions. Well, I will not develop this more than that. We can discuss this with mathematicians later on. Or, well, this is actually a comparison between the 1D case and the 2D case. Where the thickness of here it's not very clear. This is actually, this is not very thick because it's multiplied by 10 minus 3. There is a multiple, but in order to see it, because if I want to put it, it will be like the first, like the upper one. They have to be together. So in order to see that 2D converges to 1D, we render this, we multiply it by a coefficient just to be able to see it, so that as you can see, they propagate with the same speed. So the 2D, when the thickness is very thin, it converges to 1D. Okay? I don't know how much time I have, actually.
Dr. Khatib, we've got some time if you need another 10 minutes.
Yeah.
But it'd be nice
10
to
minutes?
use some time
Okay,
for questions.
okay. So, yeah, I will try in 10 minutes. Thank you, Dr. Jnani. So, well, now, as we said before, there are, let's say, two major steps in this whole phenomenon. First, the inflammation, the setup of this lipid deposit covered by the fibrous cap. Then the danger starts. What is the danger? The interaction of blood with this plaque that might lead to the rupture of this plaque. This is what we will study. So we consider that the inflammatory model set up, and we have a plaque within our artery that is deforming the lumen. And now we will study what if blood comes and interacts with this solid body, let's say, called fibrous, plaque. It's an atherosclerotic plaque. So this is a model for the blood-plaque interaction. And it's actually an FSI model. We call it FSI, so fluid structure interaction. Well, so we model the blood using the fluid equations, or if you want, similarly, Navier-Stokes equation for fluids. And the plaque here formed by fibrous cap and lipid core is modeled through monorail hyperelastic solids. And on the interface, we have equilibria of velocity and equilibria of, equation of velocity and equilibria of normal stress. On the interface, what is the interface? Actually, it's it's the interface or the boundary that is situated between the domain of solid, which is for us the plaque, and the domain of the fluid. Yani, if we go to this figure, this is representing an artery in a very simple way, with a rectangular shape. Blood enters on the left and exits on the right. And inside, it will interact every time we have a pulse. It will interact with this atherosclerotic plaque. So the interface is where they interact actually. Okay, very good. So this is the model. Well, yes, here this is a very detailed thing. I will go over it. I will skip it actually, and I will show us the simulations. So this is the result of the first simulation when we consider the blood as a Newtonian, because we can model the blood through two different ways. Blood is a very complex fluid. It's a nightmare actually, and it can be modeled in a very simple way, like a Newtonian fluid. What is a Newtonian fluid? It's a fluid with a constant viscosity. Period. While blood is not of constant viscosity. But we can do this approximation in large arteries. In large arteries, blood behaves like a Newtonian. With constant viscosity. We can do so. So this is the first simulation, and the second simulation with the non-Newtonian. And we would like to compare those and estimate what? Two quantities. The displacement, how the plaque is, let's say, pushed by the blood, and also the recirculation. As you can see here, for example, look, downstream the plaque, we have vortices, okay, recirculation. These recirculations are very dangerous. Why? Because what is a recirculation? It's a rotational motion. So in the center, it's not moving. And when blood stops moving, it coagulates. And if it coagulates, it generates a solid part. The coagulation is a solid part. So it's very dangerous because it can go and obstruct some parts of the circulatory system. And yes, the blood clot, exactly. So that's why we are trying to estimate the effect on the recirculation and on the on the displacement. And we can see, well, here also we moved from 2D to 3D. We simulated the interaction with the blood using more sophisticated and especially more sophisticated boundary conditions. As you know, this needs a high computational power in 3D, because when the mesh is, as you can see on the right, is extra fine in order to get accuracy when you simulate, this needs server simulations and maybe clusters, powerful machines, I mean, okay, in order to be able to handle this. These are additional simulations. We are as well looking at all these quantities in order to compare. Look at this, non-Newtonian flow with moving wall. So here we also incorporated the fact that the wall is elastic. لأنه the vasculature is not a rigid, مش من بطون, it's a tissue. So it can also interact with blood. Okay, so we can incorporate this with moving wall or fixed wall in order to compare what is more suitable in terms of modeling. The shear stress upstream and downstream, the atherosclerotic plaque, in order to predict. And we can see, for example, let me just state the first statement here. Von Mises stress is highly estimated in the upstream part of the stenosis if a fixed mode is considered. And the model here, as results, if we address all the data that we obtain, demonstrates the importance of vessel wall movement, because there is a big difference between consider it as elastic or as a fixed wall. Well, the last step that is currently, has been developed and submitted and accepted actually, but not yet published, is to take a real artery from MRI and put all of this knowledge inside. So this needs many things, because sometimes in the MRI we have only the interior. We don't have the thickness of the artery. So we need to construct at this point the outer layer of the vessel. We need to identify the stenosis. It's a bit, we can see here that it is narrow. Here, this is the carotid, actually, it's a bifurcation. So it is narrow. And of course, since it is MRI based, patient specific, this is taken from a patient with actually is very young patient. Very young, child, but having this, unfortunately. So, in order to simulate all these, so a lot of numerical also aspects can raise when we construct the outer layer, as you can see. So here it's the inner layer with this reduction of the lumen, and here it is when we constructed above the layer, like you can see here, the thickness. This is what we would like to do, and we would like to simulate over a real artery the blood circulation and see how artery moves, how the inside moves, because here we can render the artery outside domain or boundary to more transparent in order to see what is happening inside. Also, these are the photos of the collaborators from Lisbon in Portugal. And I would like to mention that Dr. now, Ghada Abiyunis, is our graduate from our ACM. She conducted also research, and she suggested a model of 14 equations for the inflammation. All of them, they are coupled. It's a complete